What if humanity's first computer was also the first step toward artificial intelligence? Long before the first bronze gears turned beneath the waves off Antikythera, survival depended on reading the sky. For ancient farmers, every harvest was a wager against the unknown. The rising of a single star could mean the difference between feast and famine. Fields waited for rain, but rain answered only to the secret rhythms of the heavens. To bring order to this uncertainty, people carved knowledge into stone. Parapegmata, weather calendars etched with daily omens, became the farmer's guide. Each line recorded a sign: the first song of the nightingale, the sudden silence of crows, the ring around the moon. A shifting sky became a script, and the land's fate was written in its margins. Pliny the Elder, writing in the 1st century, compiled these observations into lists that blended science and superstition. He noted that a halo around the moon warned of coming storms, and that the flight of swallows could forecast the turning of the seasons. These signs were not random. They were patterns, tracked and compared year after year, then inscribed into public tablets and recited as practical wisdom. The parapegmata served as both almanac and oracle, a primitive but essential technology of prediction. Timekeeping devices, sundials, and water clocks offered only fragments of this larger puzzle. The real challenge was to anticipate change: when to sow, when to reap, when to brace for drought or flood. In a world ruled by uncertainty, prediction was not a luxury, it was the foundation of civilization. The drive to forecast, to see the future in the sky, became an obsession, a force powerful enough to inspire the creation of machines that could capture the cycles of nature itself. This impulse to externalize memory and project it forward set humanity on a path that would eventually lead from carved tablets to gears, and from gears to code. Sailors once charted their course by the rising of unfamiliar stars. In the Mediterranean, a ship's fate could turn on the moment Sirius first appeared before dawn, a brief shimmer above the horizon signaling the Etesian winds would soon sweep the sea. These winds, blowing steadily from the north each summer, opened trading routes to Alexandria and shut them just as quickly. A captain who misread the sky risked missing the narrow window for grain or oil, losing fortunes to storms, or to rivals who sailed with better timing. But prediction was not only a matter of profit. Priests, too, watched the heavens, their eyes fixed on the lunar calendar, the festival of Artemis, the Olympic Games, the sacred mysteries of Eleusis, all demanded perfect alignment between ritual and the cycles of the moon. A single miscalculation could throw an entire city's ceremonies into confusion, eroding trust in the gods and in the order of society itself. To synchronize the human world with the cosmos, both mariners and priests relied on mathematics as much as myth. Tables of star risings, lists of eclipses, and complex calculations of lunar months traveled from Alexandria's libraries to the hands of those who needed them most. The heliacal rising of Pleiades or Antares, the sudden darkening of the sun, the measured intervals of festival moons, each became a data point in the ancient world's first prediction engines. Yet these tools were scattered, fragile, and prone to error. What if there was a way to carry the cycles of the sky in a single device? A portable oracle, precise and tireless, able to forecast winds and rituals alike. The hunger for such an instrument was not a matter of curiosity, but of survival, of keeping commerce flowing and the sacred calendar unbroken. In this need, the blueprint for a new kind of machine began to form, one that could bridge the gap between human ambition and the shifting patterns of the universe. In 1900, sponge divers working the waters off Antikythera pulled up a lump of bronze, fused with wood and stone, from a Roman-era shipwreck. Among marble statues and amphorae, this corroded mass seemed unremarkable until it reached the National Archaeological Museum in Athens. There, curator Valerios Stas spotted the faint outline of gear teeth inside the cracked metal. What looked like scrap was actually the shattered remains of a machine, one that would upend assumptions about ancient technology. Dating the fragments relied on radiocarbon analysis of the wooden case and the ship's cargo. The evidence pointed to a creation date from 150 BCE to 100 BCE, centuries before the rise of the Roman Empire. The Antikythera Mechanism emerged from a world where sundials and water clocks were considered cutting edge. Yet this device contained around 30 bronze gears, some with teeth so fine that medieval clockmakers would not match their precision for over 1,000 years. The largest gear, with 223 teeth, hinted at a complexity that seemed out of place for its era. Each wheel was hand-cut, axles sleeved in bronze, tolerances measured in tenths of a millimeter. The alloy, a careful blend of copper and tin with traces of lead, was chosen for both strength and workability. Metallurgists found evidence of repairs, soldered teeth, patches of fresh bronze, signs that the mechanism had been used, broken, and fixed again by skilled hands. Greek inscriptions covered the surfaces, densely etched instructions and labels. The front plate listed cycles tracked by the device: the sun, the moon, eclipses, and the 4-year Olympic calendar. The back plate offered operational guidance, directions for turning the crank, and explanations for the spiral dials. These texts revealed a machine built to synchronize celestial cycles, encoding the mathematics of the heavens into metal and motion. Who built it? And for what purpose? The fragments offer no names, only the echo of knowledge nearly lost to the sea. The Antikythera Mechanism stands as a question in bronze. How far did ancient intelligence reach, and what else remains forgotten beneath the waves? A single turn of the Antikythera Mechanism's crank set ancient gears in motion, bronze teeth shaped by hand, calculating the future with mathematics cast in metal. The device encodes the Metonic cycle, a 19-year span matching 235 lunar months using a 127-tooth gear meshed with a 32-tooth pinion. This arrangement lets the mechanism track the shifting relationship between sun and moon, predicting eclipses and aligning festival calendars. On another dial, the Saros cycle appears, 223 lunar months, or about 18 years, after which eclipses repeat in nearly the same sequence. These numbers are not guesses, but the result of generations of observation, distilled into ratios and built into the machine's heart. For centuries, the purpose of these fragments remained a mystery. In 1974, Derek de Solla Price, a historian of science, published the first thorough analysis of the gear trains. He revealed the device's complexity and its purpose, to forecast celestial events with a precision unmatched until the Renaissance. Price called it a calendar computer, a phrase that challenged assumptions about ancient technology. Could minds from 2 millennia ago have engineered a machine capable of mechanical prediction? Decades later, Tony Freeth and Mike Edmonds brought new tools to the puzzle. Using high-resolution computed tomography, they mapped the hidden gears and read inscriptions lost for centuries. Their scans confirmed Price's suspicions. The gear ratios matched the Metonic and Saros cycles with remarkable accuracy. Greek inscriptions on the plates explained not only how to operate the device, but why, describing the logic behind the gears, the meaning of each dial, and the way to synchronize the human calendar with the rhythm of the cosmos. Each gear preserves memory, each ratio encodes prophecy. With every rotation, the mechanism transforms curiosity into mechanical certainty. The Antikythera Mechanism stands as the world's first analog prediction engine, bridging ancient mathematics and modern algorithms. In the silent mesh of bronze, the origins of computation emerge, a reminder that the quest to predict the future began not with code, but with gears, ratios, and the enduring desire to understand time itself. In 1642, Blaise Pascal, just 19 years old, assembled a box of brass wheels and cogs, the Pascalane. It could add and subtract, grinding out sums for his father's tax office. Each digit turned a gear, and with every click, calculation moved from mind to metal. The machine's logic was mechanical, but its ambition was philosophical, to capture arithmetic itself in a system that never tired, never forgot, never erred unless its gears slipped. In the late 1600s, Gottfried Wilhelm Leibniz took the next leap. His stepped reckoner introduced a drum of staggered teeth, able to multiply and divide. But Leibniz's vision stretched far beyond numbers. He imagined a world where every thought, every argument could be reduced to a sequence of symbols, where reason itself might be rendered in binary, a language of ones and zeros. In 1703, he published a treatise on the binary system, writing that this was the arithmetic of the universe, echoing the ancient I Ching. The idea that all complexity could be built from simple opposites, yes and no, on and off, would one day become the foundation of every computer, every digital mind. Centuries later, Charles Babbage pursued a dream even grander, a machine that could not just compute, but tabulate the future. His difference engine, begun in 1822, was designed to automate the laborious work of calculating astronomical and navigational tables. Rows of metal wheels encoded difference tables, letting the device predict the next value in a sequence. A mechanical prophecy. Though Babbage's engines never reached full completion in his lifetime, the blueprints survive. Columns of gears, levers, and carry mechanisms, each step a physical manifestation of logic and memory. With these inventions, the act of prediction shifted from the patterns of the stars to the machinery of mathematics. Gears no longer simply mirrored the heavens. They began to manipulate symbols, to process information, to anticipate outcomes. The leap from ratios to representation had begun. Binary became the hinge, the bridge between the tangible and the abstract, setting the stage for a world where thought itself could be engineered. In these early machines, the seeds of artificial intelligence lay dormant, waiting for a new era to awaken them. In December 1947, inside Bell Labs, John Bardeen, Walter Brattain, and William Shockley pressed a wire to a sliver of germanium. The first transistor switched on. No moving parts, just electrons jumping through a crystal. Smaller than a fingernail, it could flip between on and off in millionths of a second. Circuits shrank, multiplied, and logic escaped the limits of gears and relays. Suddenly, millions of switches could fit on a single chip, each one a silent yes or no, echoing the binary dreams of centuries past. With the transistor, prediction itself changed. Early mainframes like the IBM 701, packed with thousands of these new switches, tackled problems that once took teams of human calculators. In 1954, the 701 ran some of the first operational weather forecasts, processing atmospheric data and equations to predict tomorrow's sky. What once took days now took hours. The future, once written in the slow turn of gears, now flickered in the pulse of silicon. But the leap wasn't just speed. In 1943, Warren McCulloch and Walter Pitts had published a model of the neuron, a logical unit that fired if enough signals arrived, silent otherwise. Their threshold neuron was simple, binary, and familiar. It offered a mathematical blueprint for building minds from switches, suggesting that intelligence could be constructed from the ground up. Transistors and logical neurons together opened a new horizon. Machines that could learn, adapt, and predict at a scale no gear train could touch. The dream of encoding the world's patterns, once hammered into bronze, now flowed through rivers of electrons. Between ancient gears and modern artificial intelligence lies the story of civilization's urge to predict and to understand itself. A question echoes through every corridor of modern life. How much of the world is now predicted by machines? Each time a language model completes a sentence, it is calculating the most probable future word, drawing on patterns distilled from billions of examples. In 2017, the transformer architecture changed the logic of language forever. Its core mechanism, attention, lets the model weigh every word in a sequence, mapping relationships across entire paragraphs, stories, even cultures. The result is a statistical engine that writes, translates, and reasons. Its accuracy is measured in perplexity. The lower the number, the more certain the forecast. Weather, once the domain of omens, now unfolds inside supercomputers. The European Center's ensemble runs 51 simulations at a time, each a possible future. Their spread revealing the limits of the uncertainty. These models do not just predict rain. They anticipate the dance of hurricanes, the flicker of jet streams, the arrival of drought years in a warming world. Streaming platforms, too, are built on algorithms that learn what you might want before you know it yourself. Netflix's recommendation engine tracks every click, every pause, every abandoned show, refining its predictions with each new data point. The metric is click-through rate, a number that measures how well the machine knows the watcher. Everywhere, statistical models anticipate language, climate, desire. The world is becoming a web of prediction, each system a silent oracle, forecasting not only the weather or the next word, but the shape of human attention itself. Are these tools, or are they the first signs of something more? When machines begin to predict us, do we remain their masters or become the predicted? A car navigates a city street, its sensors feeding a neural net that predicts every pedestrian's next move. 30 milliseconds, that is the time it takes for the system to see, decide, and act. In those fleeting moments, the world is reduced to a cascade of probabilities. A cyclist might swerve, a light may flicker from green to red, a child could dart into the crosswalk. The vehicle's digital twin, a living model of its every part and environment, runs in parallel, simulating wear and tear, predicting failures before they happen. In factories, these twins have cut unplanned downtime by a fifth, saving millions each year. Yet for all their power, these systems remain tethered to patterns. They see trajectories, not intentions. An autonomous vehicle's neural net can map the arc of a ball rolling into the street, but it cannot ask why the ball is there, or what it means to the child who follows. The philosopher Daniel Dennett once said, "A gear is a pattern recognizer of motion, a neural net is a pattern recognizer of data. The leap from motion to meaning is not automatic." This is the grounding problem, the gulf between recognizing patterns, and understanding their significance. A digital twin can forecast a turbine's failure, but it cannot grasp the human cost of a blackout. Prediction, in these dynamic worlds, is both a triumph and a limit. Machines can anticipate the next move, but do they know what matters? As we build ever more autonomous systems, the question lingers. Are we creating tools, or the first flickers of something that will one day interpret, not just predict, the world around us? Prediction now stretches far beyond the weather or the turning of the stars. As artificial intelligence approaches the horizon of generality, the question is no longer just what machines can forecast, but who or what they serve. Alignment becomes the watchword. Will these systems reflect human values or drift into alien priorities of their own? In the search for perfect prediction, humanity risks building tools that slip from our grasp, shaping futures we can neither foresee nor control. Civilizations have always left their memory in artifacts. The Antikythera Mechanism survived by accident, a relic sealed in darkness for 2,000 years. What will remain of today's predictive machines? Data centers hum with models that simulate economies, ecosystems, even the behavior of entire cities. Yet silicon decays, code corrupts, and digital knowledge can vanish in a single lost backup. If future archaeologists unearth the ruins of our servers, will they see the outline of intelligence, or only the shadow of forgotten ambition? Some theorists imagine a world where prediction itself becomes the engine of civilization, a planet run by digital twins, climate simulations, and autonomous agents anticipating every need. Others warn of simulation theory, the idea that our own reality could be a computation, nested inside another. These are more than philosophical games. When machines begin to predict us better than we predict ourselves, the line between tool and successor blurs. Are we building servants or sowing the seeds of our own replacement? Will our legacy be wisdom or a cautionary tale of intelligence lost and rediscovered? Thousands of years ago, humanity built a machine to predict the heavens. Today, humanity builds machines to predict reality itself. And somewhere between those ancient gears and modern artificial intelligence lies the story of civilization. Civilization stands at a threshold. Our machines now forecast the world with uncanny precision, sometimes outpacing our own understanding. What happens when algorithms predict us better than we predict ourselves? Are these tools, or the blueprint for successors? If history is a cycle, will our digital oracles someday be lost, awaiting rediscovery? Thousands of years ago, humanity built a machine to predict the heavens. Today, humanity builds machines to predict reality itself.